Good afternoon, everybody. We are here on the second lecture on lesson number 3 of your curriculum. We are under the section called Numerical Descriptive Measures, where we are going to discuss the central tendency and dispersion of data series. So we have covered so far two preliminary sessions. The first one was on the very beginning of what we did on the introduction to statistics. The second, we focused on the collection of data, sampling methods, and the presentation of such data in an organized and an appealing manner, rather visual manner, for decision-making purposes, and also to communicate some message to the audience. Having finished those two sections, we started this lecture series on the central tendency and dispersion, where we are trying to give some characteristics to the collected data, which, let's see whether, I believe I'm audible to everybody. I'm sorry, I couldn't check that. Okay. Yeah. So having finished those two sections, now we were at a junction to give some characteristics to the collected data. We are going to identify some of the key indicators which will define the shape of a particular data set, or which will give some identity to a data set. By defining those unique characteristics, we should be able to compare or contrast two collected data sets and do some evaluation and identify which one is the better, and identify which one will give you a better yield or a better return or a least cost. So those kind of judgments you could take by identifying those characteristics, identify how to compute them, calculate them, and also the limitations when you're going to use them. So before we go to the lecture 2 on lesson 3, I think we stopped at a junction last week where we couldn't discuss all the questions that we were planning to cover during the session. However, we discussed quite a extensive depth of theory under the central tendency and dispersion. So I'd like to take a minute and go back and go back and discuss a little bit again onto what we discussed under lecture 1 of the session 3, because that, of course, these two lectures are combined hand in hand, where you will be able to find a lot of interrelationship between those two lectures from inception to the latter point. So there'll be one slide at the last of the today's lecture which will depict all the important equations which you need to keep in mind when you are going to sit for the examination. Okay, so we first discuss that the difference from the descriptive statistics to the inferential statistics. We try to identify what descriptive statistics are, and finally we came to a judgment that we are going to explain the complete data set using a sample, where we are going to call it as inferential statistics. So in the sampling techniques also, we identified that the basic limitation would be that in most of the cases we won't have access to the entire population. So that's why we will be always depending on a sample to collect data and analyze them. So under central tendency, we discussed three most important concepts: mode, median, and mean. Briefly, we'll go through one by one. Mode would be the most frequent score for the value in a given data set. Median would be the middle point of the data set when we put them in an orderly manner, an ascending manner. Last on that three, the mean would be one of the most ideal measures to represent a data set, where we are collecting, or rather will be taking the sigma of the weights or the numerical values of individual items in the data set, and we'll be dividing them by the number of items to uh, calculate the mean. Hereinafter, we identify that we need to define whether we are going to discuss this data set under the term of population or sample. It's very important to note that whenever we are going to discuss the population, we will be denoting it with capital N, while when we are going to discuss the same measures with the sample, simple N. And later down the line, we are giving two names also for the sample and population. So that I mean, there could be any other naming also. However, I have selected row and S to the population and sample. We'll discuss that also. We discussed that if you have been given a mean for a particular data set, uh, and if you want to combine them all together, data set 1 to data set K, you could multiply. I mean, you could take the addition of the multiplication between the number of items and the mean of a given data set, add them together, divide by the number of items, will give the accumulated mean for the 1 to kth data set if you have been given that sum to resolve. Um, discuss some of the advantages and disadvantages of mean, median, and mode. We recognize that some of these theoretical points has been questioned quite often at the examination. We identify where each of these three measures are appropriate, means, median, and mode, in their own way. It doesn't mean that mean is the best and we shouldn't look at median and mode ever. It's not the case that we are using these three measures in some unique instances as and they occur. Then we, after focusing on the central tendency, then we came to the latter section of the last week's lecture that was on the dispersion. Dispersion, the basic idea of dispersion is the scattering of data around a central point or an interested point in a given data set. We identified that there are three measures that we can discuss under the dispersion. That would be range, mean deviation, and most important, which will be taking into consideration heavily during today's lecture, that would be variance and standard deviation. Range is a no-brainer. That would be the difference between the largest value and the smallest value. That will give you a very brief idea as to the data being scattered from the minimum point to maximum point. If you've been asked to compute the range, that would be the difference between the maximum and the minimum. The mean deviation was the foundation or the stepping stone for many of these computations. This is where we are going to take the difference between individual point to that mean. So if we are trying to calculate the mean deviation for a data set with both positive values deviating from the mean and the negative values deviating from, they will be cancelling them off each other and will be come up with a mean deviation of 0. So to resolve that only, we are taking the modulus or the positive value of these deviations. Having discussed mean deviation, we came to the point where we define variance and standard deviation. So this is what we discussed at the beginning. Whenever we are going to discuss indicators on the sample, we'll be using S, and with that the same for the population, the sigma. The variance and the standard deviation are the stepping stone for the other equations that we are going to learn today. Both are same indicator defined in a two different manner. Variance is what we calculated, but when we calculate variance, we'll be taking the we'll be converting the data set into a different level of the original form. That's why we take a square root of the variance and come to the standard deviation. Let's quickly look at those two equations. For the moment, just forget about this ungrouped data. Focusing on the group data, instead of taking the modulus for the variance, what we did was we took the difference between individual value to that mean and we took the square of that particular value and divide by capital N. That's the number of items. When we want to define the standard deviation, same value of the variance, just we took the square root. So basically, the variance and the standard deviation are pretty much same, except for the fact that standard deviation will always give the value in the same plane of the data will be lying, while if you're talking about the variance, it will be defined in a different plane or a phase. That you don't have to worry much on that. So sorry, I have highlighted in red here. This would be the most popular equation we'll be using across throughout the questions and the examinations point of view, where the data set, variance, and standard deviation for a sample, it's very important, sample will be defined by these two equations. There also, we discussed something very important last week. In contrast to the population, where the number of items are capital N, in contrast to that, when we are coming to the sample, variance, and standard deviation, we are not dividing by the simple n, rather, we are dividing it by n minus 1. You can discuss under degree of freedom of data set that why by dividing n minus 1, we are taking a higher variance and higher standard deviation, obviously. Why that is stemming will be, could be discussed under a different context. However, this is, the essence of this lecture series would be to give you a glimpse on the applicability of these equations, rather proving them and defining them is somewhat different from the discussion what we are going to have today. So keep in mind of this fact also. If at all the question says on the population, you have to take the number of items, the capital N. But if the question says we are looking at a sample, or if the question implies that we are looking at a sample number of days, sample 5 days, sample week, that implies that you have to be careful and divide it by n minus 1. That's an important point. I think we discuss that for this given data set, the calculated values of sample variance and sample standard deviation last week. We identified that the characteristics, advantages, disadvantages of these measures. And finally, we stopped last week's lecture with this important concept, where if we merely look at the variance and the standard deviation of a given data set, and when we are trying to do a comparison, that will be leading into misleading interpretations due to the nature of the two data set that we are comparing. Maybe due to the scale, maybe due to the number of items, maybe due to the collected method. It could be various. It could be various reasons that will be giving that misleading judgment. So, rather comparing those data in an absolute manner, we discussed last week at the finalization stage that we could take this coefficient of variation, COV, by just taking the ratio between the standard deviation and the mean and compare the coefficient of variation between data sets to identify different characteristics of two or more series, whether which one would be the least cost, which one would be the highest yield, likewise. I think, yeah, this is where we stopped last week. I think we wanted to see by calculating the coefficient of variation between these two data sets. The first one would be capital X data set to capital Y data set, to see that you may end up with a similar standard deviation. However, when you calculate the coefficient of variation, you could see that it would be indicative values which will define the nature of the data set. But merely if you just take the standard deviation, if I just take the question 1 and try to discuss the standard deviation, I think we came across the answers of SD for X would be 1 and SD for Y also would be 1. However, if you look at the data set, X will be comparing the standard deviation of X will give you the entire range has been covered by a one standard deviation. However, if you look at Y, we are looking at a minor deviation from 101, 102 to 103. Here, from 2 to 3. So when you compile the coefficient of variation, coefficient of variation for data set X, you should get the value of 0.5. It should say it's a more variation scenario compared to coefficient of variation Y. It should give you a value of 1 over 102, which should be equal to 0.0098, which implies a less variation. I hope you may had a chance to country A versus country B. This will be for a fuel price. Let's say this data set will be from Monday to Friday, the fuel prices of country A to country B. So, I mean, maybe a different scenario to Sri Lanka, but we could assume that depending on the respective regulations from a day-to-day variance of fuel changes could be certain case. So for the same data set, if you do a compilation of variance and standard deviation and the coefficient of variation, you may identify that country A to country B, which country would be having the more variation. So this would be a practical application. I believe we stopped here, and we did not have much time to discuss the question papers. We had plenty of MCQ questions. Some questions you could recognize that it may have been repeated. However, the concepts that has been tested in those questions are very important. So the plan for the day is we'll be starting today's lecture on the second part. So we have covered, if I recap the inception, we have covered the central tendency and dispersion of a given data set. Now we are going to move into a few more advanced concepts on the variability. So today's contents, what we are going to cover on skewness and courtesies would be on the first segment, where we'll be only looking at one variable. It's very important, one variable. When we're discussing the skewness or the courtesies of a particular data set, it implies that it only contains one variable. I mean, statistically, there could be multivariate analysis for skewness and courtesies also, but for the learning purpose, we'll be discussing those two linked to the single variable. And under covariability, section 3 here, we'll be introducing two variables just to see the covariability between one variable to another variable. We'll be defining independent variable and depending variable there, and we'll be learning to compile covariance, correlation coefficient, and wind up for the day. So if we have time, I'll show you, I mean, in fact, during past paper question, which will come of the discussion today. And hopefully what we are planning to do would be, since we have a 1 or 2 day advantage, we are ahead of the schedule actually. So the next day we will again brush up the theories one more time, and we'll spend a good 1 to 1.5 hours to discuss all applicable exam questions, both structured questions, by again refreshing this area. Okay, that's the plan for the day, and we'll start the session by again coming into the continuation of the last week's lecture on central tendency and dispersion. Okay, so what was the purpose of last week's lecture? If I just try to recap, that was to identify for a given data set whether could we define one or two indicators to represent the data set, or could we come to conclusions on one or two important numbers which will be the representative for that data set, which will be the middle point of that data set, and how vary on average a given data from that middle point, from that average point. That was the whole idea of last week's lecture when we want to discuss the central tendency. Now, the first concept that we are going to touch upon today would be a concept called skewness. The extent, it is apart from symmetrical shape. This is known as skewness. So we'll see what do they mean by this symmetrical shape and the extent it is moving away from that symmetrical shape. So that is the whole idea which you need to understand. They're discussing on a symmetrical shape and they're discussing again on moving away from the symmetrical shape. So when you go to the graphical definition, you will see what do you mean by skewness. But for the moment, let's try to grab these three concepts. Skewness can be discussed under three circumstances. We could identify either normal distributions. So then this normal distribution would be the symmetrical shape that we are going to talk here. And if the normal distribution is not skewed, then obviously there will be two skewed scenarios, either positive or negative. So that's what is meant by here. In nature, we could identify positively skewed distribution or negatively skewed distributions. We'll have a graphical look in a while. So the positively skewed distribution. Now, okay, I'll take the board for a moment. Okay. Now, before we move on to the positively and negatively skewed distributions, we'll try to see what do you mean by a distribution. Now, under next lecture series on regression and few more areas to come under like probability, we'll be extensively using the concept on the normal distribution and the distribution heavily. If you plot the data, sorry. Yeah. So if you plot the data set on an x-axis for a single variable, let's say you have data 5, 6, 9, 10, 11, likewise. And then on the other axis, on the y-axis, if you plot the frequency of occurring of data, you could either draw bars like this, or you could simply connect those bars like this. So in simple terms, when prior to we are discussing the skewness, when we discuss the term on a distribution, the whole idea will be a variable will be having frequencies of their occurrence being plotted to two axes of x and y will give you a distribution. This is about it. So now if you just forget these numbers and if you just forget these occurrences also. So what do you mean by a normal distribution would be a graph with a shape like this. So in last week theory, we discussed that in the data set, if there is a maximum number of occurrences, we could recognize that point as the mode. Let's say in this given data set, the average mean will be somewhere over here. Mean. And the middle point, the median, I mean, I'm just hypothetically just trying to draw here, will be somewhere over here. It could be here, here, it doesn't really matter. So what I have drawn here are three important things which we discussed last week under central tendency and dispersion, where graphically we could identify that the value for mean, the value for median, the value for mode could be graphically drawn and identified and marked like this in a given distribution. So ideally, if you look at a normal distribution or a non-skewed distribution, logically these values should be coming and merging to one central point. So mathematically, mode, mean and median will be similar or will carry the equal values in that instance. So this is the idea on a distribution, and this is how you could plot the values that we discussed last week. It should be mode, median and mean in graphical format with their respective values on the other axis. So having discussed on the normal distributions, now let's look at what you meant by the positively skewed distribution. It's not difficult to understand. Now this axis, which I haven't drawn here, will imply that this is a distribution of given data set, which will have the axis on this side, the x-axis, which will carry the individual values of the distribution. Now, similar to what we discussed a moment ago, in this data set also, we can earmark and identify the three central tendency indicators which we discussed last week. Those are mode, median and mean, like given here. So let's discuss what the positively skewed distributions are. If a smooth frequency curve of a distribution falls with a longer tail towards the right side from its maximum point, the peak. What is the maximum point again? Always it is the mode, maximum number of occurrences. Okay. If a smooth frequency curve of a distribution falls with a longer tail towards the right side from its maximum point, then such distributions are called as right skewed or positively skewed distributions. Majority data points will have lower values than average. So let's see how you can easily identify where these values will be lying. Okay. So like we discussed in the classroom example, with the maximum frequency being occurring on the y-axis, you can, the first one to identify in this shape would be none other than mode. Any given distribution for a single variable, you could earmark the mode like this. So having identified the mode, the only thing to remember in this jargon would be that mean value will be either going towards the right side, or under the next one we'll be discussing the mean value will be coming towards your right hand side. Having defined the mode and mean, always the median value will lie in between. What is the idea of the median? Would be the 50-50 point when you put all this data in an ascending manner. So the 50% of the data will be lying from this point to the median, and the rest of the 50% from the median point to the maximum point. The mean will be the statistical arithmetic average which will be calculated and derived. Mean may not be an actual value, irrespective to such of mode and median. Okay. We'll discuss a classroom example, but for the completion of the segment, let's see what the negatively skewed distributions are. This is the other extreme from the positively skewed or the right skewed distributions. It's the other end. The data set has been moved towards the right hand side from the central point or from the middle point. The definition is like this. If a smooth frequency curve of a distribution falls with a longer tail towards the left hand side. Now, this will be the y-axis, which we haven't earmarked here. Longer tail towards the left hand side from its maximum point. Again, what is the maximum point? That would be the mode or the peak. Then such distributions are called left skewed or negatively skewed distributions. So again, let's look at these three characteristics. Now this one, we identify that mode is the highest frequency. We define it first, and then keeping the median aside a little bit, we discuss the mean value will be either going towards the extreme tail end or it will come to the other tail end because the distribution has been skewed now from its original position. So similar to this previous example where the median will be in between the mode and mean, in the negatively skewed distribution also, you could easily identify the relationship that median value will come in between the mode and mean. So if you look at the values of these three instances, median will always lie between, but the mean value has a highest value, median in between, and the mode will be the lowest in case of a positively skewed distribution. While the only difference between this and that will be the median will be here, mode and mean will move to the cross point from one another. It's important to grasp that what these positively and negatively skewed distribution are and how to quickly identify where the mode, median, mean values will be in a given circumstance. Because if you look at the previous examination questions, it's a popular area to test your knowledge on the positively skewed, negatively skewed distribution and which value is higher than the other in a statement or in an MCQ option. So you don't have to panic if you see that. The best would be to quickly draw a diagram and apply what we discussed. You could earmark the mode first, then just have the memory that median value will always come to the in between the mean and mode. So you can easily derive the third value of mean. Either it will move towards the tail, left tail, or the right tail. If the left tail is flatter, we could say it's negative. If the right tail is flatter, we could say it's a positively skewed distribution. Now in practice, do you think we could see these kind of distributions? I would say one good example would be your advanced level marks for some of the subjects, which will be having a bit of a difficult examination question. One classic example which I can quote would be the marks for advanced level chemistry for a given student population or a sample in that case. If you look at the frequency here, you may find that if the exam paper is quite fair to everybody, you could find that it will have a shape like this. Approximately in between values like 45, 50, you may see majority will lie in this area. However, in practice, in most of the years, if you look at the actual marks and if you plot them in the graph of frequency, you could see, technically you could earmark 0 here and the maximum 100 here. You could see some of these distributions will have values like this. So the average values, three average values that we discussed, or rather the central tendency, the mean, median, mode will lie somewhere over here, maybe approximately 35, 37 kind of a range. So in most of the years, if you just plot the chemistry marks for mathematics students, you may see a distribution like this. On the other side also, if you could see an easy exam paper for any subject for that matter, you may see a negatively skewed distribution. But majority of the state exams, ordinary level, A level, if you actually plot the marks of the students, you may see skewed distributions in compared to the normal distributions. So that's the discussion on the skewness. You could identify normal distributions if you take millions and millions of data and plot them in a graph. However, depending on the nature of the data scatterness, you may see positively and negatively skewed distribution in practice. The important point to carry away would be we need to identify how mode, median, and mean shall be defined and which value will be higher than the other. This is what we discuss. We don't want to take more time here. If the distribution is symmetrical 50-50, you may see mean, median, and mode will be almost overlapping to each other. It will come approximately to near similar values. Mathematically equal values. Mean equals median equals mode. That's what we have written here. In a symmetrical distribution, data points are neither skewed towards left nor towards right. Data points of mean, median, and mode will take the equal values. That's about the discussion on the skewness. Okay. This will be the other most statistically used move or the movement in a given data set. Now, if we recap, we very ancient discussion we had on the data collection and summarization, we discussed even very simple things like a data array, stem and leaf diagram, charts, tables, where we want to organize the data in a methodical manner for an audience. Now we are slowly moving towards plotting them in distributions where individual axes of x and y will always give you the x will give you the individual values while y will give you the frequency of occurrences of such values. When you look at the central tendency, now we discuss mode, median, mean will be almost close to each other in a normal distribution, while it could be either skewed or positively skewed or negatively skewed. One other characteristic which we have missed so far would be whether those normally distributed data are scattered extra close towards the mean, median, and mode in the central points, or such data has been dispersed away from the mean, median, and mode central tendency points. That is a broad idea of kurtosis. We spell this word as kurtosis. To go through the points, the nature of the peak or curvature of a distribution is known as kurtosis of the distribution. So we're discussing about the nature of the peak, whether the peak is having a extremely higher nature or extremely flat nature. For this also, for the skewness, for the kurtosis, there are many equations where you need to apply for a data set and derive the exact mathematical values. However, for the discussion purpose and for the examination purpose, this will be sufficient to know that the skewness and the kurtosis exist for a given data set, and we could comment statistically and mathematically for decision making purposes. Okay. Kurtosis of a distribution is considered relative to the curvature of a normal distribution. Bit important point here. We're going to consider the relative to the curvature of a normal distribution, which is a symmetrical distribution, which can take three forms, which we are going to discuss here. But let me take a moment here and explain what I meant by here. Why do we want to discuss the curvature or the curvacies of a data set only by saying we are going to discuss the nature of the so-called word curvacies in relative to a normal distribution? If we earmark this as a normal distribution, what simply we are trying to see is that the nature of this peak area. You may, let's say now this is the nature of a perfectly normal distribution we are going to discuss. In compared to this one, if the curve moves like this, in compared to this one, if the curve has a pattern like this, it's the exact similar pattern. I mean, the mean median values will be closer. However, the relative heights are quite low. So this is one form which we can compare. The peak will be lower. However, the opposite would be, and you may see a higher peak like this. So what we were discussing here is that in compared to this point of being the normal point, you may see the peak will have a flatter nature. This is one aspect that we're going to discuss. If I say this as one, this nature we could earmark as 2. Then the opposite would be, it may have a higher peak. Sorry. So the peak is somewhere over here. This would be the third nature which we could discuss. Okay. So what in the notes I have said that now we are going to compare the 1 and 2 and 3 in relative to a normal distribution. So you may get a doubt, okay, for curvacies, do we really need to compare only the cases of normal distribution? What if a moment ago we discussed that you may see skewed distributions also. Technically, statistically, you could discuss for the same, the skewed distributions also. However, for the comparison purposes, the easiest would be to compare the curvacies in contrast to the normal distribution. If I just draw one illustration here, you may see a skewed distribution like this. So for this distribution also, the curve may be like this, or it could have a higher pattern. For the other side also, you may discuss the same. Could be like this, or this. But for illustrative purposes and educational purposes, we could only discuss the curvacies in related to a normal distribution. So that is what is said in the slides. The three instances what we discussed a moment ago statistically are defined as this by defining these three words. The middle one, mesokurtic, would be the normal instance or the normal distribution, where the distribution will have a normal height or relatively normal position. In contrast, in comparison to that normal position, if the peak is having a higher and higher value, the name given for that curvaceous movement would be leptokurtic. Leptokurtic means the data points will be having a higher frequency compared to the mesokurtic point. The opposite is named as platykurtic distribution. Platykurtic, mesokurtic, and leptokurtic are the three natures that we could see in a courtesies. So what do you really mean by the courtesies? I mean, what are we going to conclude with the learning on the courtesies? Are we going to say that it has a higher frequency compared to a normal distribution instance, or it may have a lower frequency? The whole idea or the learning would be in compared to normal distributions instance, the data may have been scattered extremely towards the central tendency points of mean, median, mode, or the data will be dispersed away from the central tendency points. Mathematically, if I just again try to illustrate by using some example data, I'll write some instant three dataset examples, A, B, and C. Let's say B would be the normal instance. We are talking about a classic data set of, let's say, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is sufficient. So the data set from 1 to 9 may have a distribution like this. Okay. Start from 1, go up to 9 with frequencies like this. Let's say for the illustrative purposes, I'll put a couple of 5s here, a couple of 6 here, a couple of 4s here. Otherwise, your heights would be flat, isn't that so? So you may have 3 5s here, 2 4s here, and 2 6s here, and your illustration would be similar to here, like this. In contrast to this set, if we draw a point like 3, 2 4s, and 2 5s, and 2 6s, 7, 8, and 9. It will have a slightly lower peak. To enrich this data set further, I'll put 1 or 2 more 5s here, 1 or 2 more 6s and 4s here, so that this area will have a much more frequency. But for this data set, let's say we have 3, 4, 4, 4, 4. Let's say you have 10 4s here and 5, many 5s. Let's say you have 25 5s here, 25 5s, and again 6. You have 8 and a 9. Now this, in contrast to both of these sets, will have a curvature like this. You have many 5s, some 4s and some 6s. So the broader idea that you can get from these three distributions would be, if we identify B as a normal distribution where a nice symmetrical value view could be drawn, 1, 2, 3, 4 3s, 3 4 values, 4 5 values, and 3 6 values, drawing a symmetrical nature of a frequency curve. In contrast to that, if we have 2 4s and 2 5s and 2 6s, the height will be somewhat lower. And 25 occurrences of 5s will have an extremely high peak. So students, now you will identify that what you meant by lepto and plateau would be instances where whether you have many data points towards your central tendency points or otherwise. That would be the whole idea. If you get that idea, that would be sufficient for the learning and examination purposes. Okay. Now we finish those two sections on single variables. Like in the beginning of the class, I said up to this point, we have discussed the central tendency. Under that, we have discussed extensively on areas such as measures of central tendency, where we discussed the three key indicators of mean, median, and mode. Then we went to dispersion, range, variance, and standard deviation. Mm. So up until this point, on this section on central tendency and dispersion, what we have discussed is single variable, single x variable, or single t variable, or single z variable, any variable value for that matter. So from this point onwards, we are going to discuss what will happen in the data set that you are going to discuss has two variables. What do you mean by a variable? An indicator or a value which varies with the respective measurement of the weight. So in the class example of, if you could recall, we had 45 or 75, I think we had, yeah, 75 students in the class, and we discussed that the weights of those students. One variable, weight. A student in appearance, in physique form, may have multiple variables: the gender, the height, the weight, the, let's say, eye color, the skin tone, if you could give a value or a number for that, could have many different variables, which depending on the, I mean, biographical occurrence of that particular person, you may identify and give a variable, and then when you measure it, you could name it with the variable's name. The easiest and the most discussed one in practice would be the weight of a student population or a sample of 75. So the weight may range from 40 kilograms to, let's say, 125 kilograms. If you could recall, we want to design a chair for the class, a new chair. So we need to give those measurements to the carpenter uh, on the endurance of the chair, if you could recall. And we had one or two students who will have an outlier weight of 125 kilos, isn't that so? So for that student, if you plan the endurance of the chair, that would be, I mean, let's say that would be too extreme. I mean, not that all students will have 125 kilos, isn't that so? Only two or three, or maybe in that entire class of 100 to 125 kilos, you may only find three or four students. While the majority will have a weight approximately to 45 to 55, if my class example recalls you. So we took a decision by talking to the carpenter, said, why don't you design chairs which will endure weights of the person who is sitting to 45 plus 10 kilograms, that is 55. Now what will happen to those students with 120, 125, maybe 100? So we asked the carpenter, design 75% of those chairs with 45 plus 10, while the rest of the 25% design it to endure maybe 120 or 130 or higher values. So when the students are seating physically, we could ask them to seat appropriately with two types of chairs, which the one set will have a higher endurance and one set will have an average endurance. So by doing that, we may have taken a smart decision to cut down the cost of the chair manufacturing. Okay. Now that example, why I want to recall is that we utilize one value which varies from the measurement, or which varies from observation to another observation, by looking at a single variable. Now, let's say those same 75 students, can't they have two variables to be measured in one pair? The classic example that I'm going to quote here, and which we'll be discussing again and again in the upcoming lectures, would be two variables of weight and height. Let's say there are students of 45 kilograms to 55 kilograms having different heights. Some may have, let's say, 5 feet, some may have 5 feet and 2 inches, 6 feet, I mean, different heights. And on the other hand, also, for the average students and extremely weighted students, also, you may have different heights. So from this point onwards, so for the other areas that we are going to discuss, it is important to note that we will be discussing the values of two variables which could be measured for one data instance, one person, one observation, two variables. Important to grasp that concept. Whenever we have two variables of a given data set, which will have two variable values, we could identify the covariability of such data sets or data points or data observations. Again, I reiterate, when we have two variables of an observation, we could observe the covariability. I mean, why we are trying to do this is merely for decision-making purposes, isn't that so? So for that class example of carpenter, our chair, 75 students. So for that example also, if I came to the final conclusion, what I wanted to do is to optimize my budget. If I had unlimited budget and if I been asked to design those chairs, I would jolly well ask the carpenter to, design a chair that would even have an endurance of 250 kilos. So the carpenter will design extremely tough chairs for the students of our classroom having 75 students. But still, I may have overspent on my budget. Isn't that so? So by taking my call, I mean that 75% to 25% deviation is my call. That's my appetite. I mean, you may have 60 to 40 or maybe 55 to 45. It's up to the statistician to decide. But having decided that deviation between average and just by catering some outliers, what I have done is I have optimized my decision making process. Now for this also, the covariability, why we are trying to learn this is merely to see the pattern of variability of the data pairs from the central tendency point. And then when we come to the next segment on the regression analysis, multivariate analysis, what we are going to do will be to identify the best fit line or the trend line for these data sets of independent and dependent variables. And then by defining those, you can predict for a given independent value what would be the value of the dependent variable. You could estimate, you could derive, you could extrapolate, you could interpolate. So that is the whole idea of why we are bringing in two variables and why we want to identify the covariability of those two variables. Having said that, let's see some of the broader definitions of the covariability. So for the covariability to exist, as I explained, we need to have two variables. In mathematics and statistics, we define the independent variable with the denotation of x in the majority of the time. So the independent variable of capital X or simple x will be the value which moves independently. And on the other hand, the dependent variable of y will be the value which moves in line of the movement of the independent variable. So in our class example of weights and heights, so indirectly what I'm trying to imply here is that a student of 35 kilos, you think can he have a height of 6 feet and 6 inches or 6 feet and let's say 8 inches? It's difficult, isn't that so? So he may have an average height of maybe 5 feet and 6 inches for that case. Whereas those students who are weighing bit extreme, maybe let's say um, 85 kilos and 95 kilos, you may find some sort of a covariability between that student's weight to the height of that student. So either you may choose weight or height as the x variable, and by moving that variable around for the collected data set of 75 students, you could measure the dependent variables value in data pairs x's and y's, x's and y's, and we are going to define the uh, covariability of those two variables in the upcoming slides. We went through the notes a little more. We can identify the interrelationship between x and y by plotting the x data in horizontal axis and corresponding y data in vertical axis, which will give a scatter graph. If you could recall, during our lectures on data presentation, we denoted that you could denote the data representation of graphs by bar charts, pie charts, line charts, and then we stopped the lecture by this word of scatter graph. Now the scatter graph is nothing but when we plot those independent variable and dependent variables in a 2D graph. So when we plot those data points of the x-axis and corresponding y-axis values, there we will be getting the graph called scatter graph. When we plot those scatter points, what we could identify will be the relationships in a visual manner. So when you look at the look at a scatter graph, just by looking at it, you may see, okay, data may be centralized towards one point, or data may be having a movement from let's say an ascending order, or no pattern at all, or for the each and individual x values you may have a similar or exactly similar y value, or a curvature, or a ellipse, or a circle. I mean, the relationship could be anything. But broadly, if you want to identify the covariability, you could cluster those relationships into three broader aspects. That is what we have written here as, if you eyeball it, if you just look at the data set, you may identify either positive relationships or negative relationships. So the third one, where you can't visually identify any relationship. Let's go back to the board and take a moment and see what a scatter graph is and what sort of relationships that we could denote from it. Okay. Yeah. Just quickly change that. Now we discuss, for the covariability, we need to identify the independent variable, which we will be denoting by the symbol x, and the dependent variable of y. Now the data points will be having the nature of x to y. A classic example could be x value will have a numerical value of 3, while the y value will have a numerical value of 5. This will be one form of representation, x to y. It's a pair. For the independent value of x, you have 3, while for the same data point, you may have a dependent variables value of y. This may be the weight, this may be the height. Okay. So the whole idea of we are trying to plot the scatter graph is where you put 0 here. You could plot those points either by crosshairs or circles or triangles, it doesn't really matter. You could plot those points like this. So for individual x value, you may have a y value. So for another individual independent x value, you may have a y value. That's the idea. So in that example, this is 3, this is 5. Okay. So these will be the plotted points. So the idea is that when we plot those points of independent variables and dependent variables, we are going to eyeball it. We are going to just look at the data set and see whether we could identify any relationship between these two variables of x and y. Now I'm going to jump to this conclusion. Before we go into the theoretical part, I'm going to jump to this conclusion and say it seems to be that for the independent variables of x, we seems to be having a positive relationship of similar to what we have drawn here. In mathematics, what we could say is that for the smaller values of x, you may have smaller values of y, while for the higher values of x, you may have higher values of y. So it seems to be scattered with a positively related manner. So that is the whole idea of So that is the whole idea of relationships that we are going to discuss under here. So when we plot the data in a scatter graph, either you may see positive relationships, negative relationships, or no relationships at all. So what we are going to measure again here would be the value of covariability. Let's look into these. No relationship, we don't have to discuss anything. We are not deriving or coming into conclusions by identifying no relationships here. Rather, the positives and negatives will be the useful ones for us to make decisions. The positive relationship could be observed when y variable are increasing in line with the increase of x variables. This is what we discussed a moment ago. If the x variables are increasing from 0 to towards the positive side, in a similar manner, the y variables values are also increasing. For the smaller values of x, you may see smaller values of y. Or for the higher values of x, you may see higher values of y. But for this also, this positive relationship also could be denoted in different circumstances. If you carefully look at these 3 scatter graphs which we introduced a moment ago, the trend, or if you just try to put a best fit line in our basic grade statistics, we learn something called a best fit line, where you just eyeball these scatter points and try to draw a point which will do justice for all these points by using a ruler. If you look at these 3 scatter graphs of from left one and the middle one and the right one, you may see, okay, under the covariability, we could recognize that this will have a positive relationship. However, if you further look into the positions of the scatter points which are here, you may recognize that this instance has a perfect positive relationship. That means from single point to the next point, if you put up a ruler and try to draw a line, almost all these scatter points will be crossed or will be intersected by the ruler's values. But coming to the other 2 points of strong positive and weak positive, what we would say is that you may draw a line like this, and similar to the board example what we discussed, you may draw a line like this. However, you may not see that majority of the data points are being represented by that line. Coming to the last point, your line may only cross maybe 2 or 3 points. So what's the whole idea? Let's say for the independent values of x and y, if given in this perfect positive relationship scenario, if we could identify this line y equals mx plus c or y equals ax plus b or c, if you could identify that line, what you can do is for the next independent variables value, you can predict perfectly what the value of the y variable will be. Isn't that so? However, in contrast to that perfect positive relationship, the left corner side, however, in contrast to that, how about if the data set has a weak positive relationship? Would you, by comfortably say that, for the weak positive relationship, you are going to exactly get this value for the y? It's quite difficult, isn't that so? So that's the idea of identifying the, the extent which the positive relationship is being evident. The three instances, I repeat, would be perfect positive relationship, strong positive relationship, and weak positive relationship. Similar to these positive relationships, you may see a different scatter graph in the instances that we have plotted here. Now in this instance, it's quite evident that when the x values are increasing from 0 towards the uh, extent of maximum values, you may observe that when the values of independent variable increases, the value of depending variable or y increases as well. In contrast, negative relationships are where you could observe when y variable are decreasing in line with the increase of x variable. I repeat, y variables are decreasing in line with the increases of x variables. So you may observe that three instances that we are going to discuss here of perfect negative, strong negative, and weak negative are exact opposite to these three positive relationships where your x value increases with y value. In here, your x value decreases with, the y value decreases with the increase of x value. But similarity between these two instances would be the degree or the nature or the strength of the relationship of the three data sets of perfect, strong, and weak will be similarly identified or vigilant or observant in the weak or negative relationship, the negative relationship instances also. We could look at the data scatteredness. Perfect negative relationship will have the trend line or the best fit line crossing each and every point that will be lined here, while the strong negative relationship towards somewhat, while the weak negative towards the best fit line will cross maybe 20% or 30% of the data points that will be in this catagram. To sum up, the relationships that we are going to discuss under covariability will have positive or negative relationships, and the degree or the gravity or the strength of the positive or negative relationships will have perfect, strong, and weak as the three instances defined under the statistics jargon. So the 6 instances where you may see the scatter graphs that we are going to discuss would be perfect positive relationship, strong positive relationships, weak positive relationship, perfect negative relationships, strong negative, and weak negative. The 7th would be what would be that? Positive, negative, and no relationship instance. It will be the scatter graph will have a crosses and dots and whatever the marks that you are going to denote everywhere without any indication of a positive or negative relationship. Okay. Moving on, now we are coming to the important segments of today's discussion on identifying the covariability. Now, if I recap some of the earlier lessons that we learned for single variables, we discussed variance and standard deviation. Under the variance and standard deviation, what we learned so far was that how deviated your individual given points of the data set from its mean or from its central tendency point. So for this covariance discussion also, you may see the similar concept being applied. However, the only difference is now we have two variables. Okay. So uh, by using the single variable equations, the statisticians have denoted and have defined these equations of covariance. In future, we're going to learn the coefficient of covariance, coefficient of determination, we call it the R square. All these are extensions that is stemming from the single variable equations. However, again, I reiterate, you will be not asked to categorically define how each and every is equation that we are going to discuss under the examination is going to be evolved, or rather only the applicability in a thorough and a concise manner. So the important point would be to identify the points where you need to keep an eye on things like whether we are going to apply this the data set on the sample or the population. So depending on that, we may see instances of let's say n or n minus 1, or whether we are going to have a single variable or two variable instances of x's and y's. Okay. Coming to the equation of covariance, let's go through the theory a little bit more. It is a measure of how much two variables vary together. Previously, it was a measure of how a given variable vary from its mean. Now, in this point, what we are going to learn is that given two variables, this is a measure of how much two variables vary together. Covariance of sample capital S and population rho can be calculated using following formula. This is small. I apologize that this red box should be coming towards this area which I want to highlight. This is just the illustration of the individual values that I'm going to discuss. What I want to highlight by red are the equations that you need to keep an eye on, keep remembered, and keep applying at the examination. Okay. Having said that, let's look at these values, what they are, before we move on to the applicability of the equations. So the rho and the S square, if you merely look at the difference in a glance, you may recognize that for the population, you should divide by n, while for the sample, n minus 1. That's the only difference between these two. So forget about the population. What we need to keep an eye on would be the sample, this highlighted area. So the covariance in statistics is being denoted by S square. Okay. For the previously learned variances, S square was the same, but it didn't have x, y, or x for that case, because we indirectly implies that S square for one variable. But for given two variables, it's important to write S square for x, y. Or in your example, if it is P and Q, S square for P and Q. What is meant by S square would be covariance. So the idea of this sigma we discussed last week, this would be from I equals 1 to the nth item, simple nth item. Okay. So the x bar and y bar are the values of nothing but the averages or means of the independent variables. If you put up all the independent variables in one row in an ascending manner, add them up, divide by simple n, will give you the values of x bar and y bar. Okay. Having said that, xi and yi are the values of individual observation. Let's say in that example, I had x of 3 and y of 5. So xi would be 3 and yi would be 5 in that case. So the whole idea of this equation is that what you need to do is to take the difference between individual x value for the average of that variable's value multiply by individual y value for that average of the that axis's values, and take the summation or the sigma of those individual observations. Let's say for simplicity, I'll use the board here. Let's say for simplicity, we are talking about 5 data points here. In that instance, what you need to do, okay, I'm just going to introduce some 5 data points here, xi and yi, in the form of like this 3 and 5, 7 and 3, -1 and 4. Can we have negative values? Of course. No harm. 0 and 3, 10 and 4. Okay. These are the 5 values that will be denoted by these i's. So this is I equals 1, I equals 2, I equals 3, 4, and I equals 5. So given this data set, what you want to do here will be take you have to first compute the x bars and y bars for this to calculate manually. If I take a moment, these are the values of x variables, isn't it? These are the values of y variables. So merely what we are going to do will be to calculate the x average, y average, and take, let's say hypothetically we get x bar as 3 and y bar as 4. In that case, for this point, what we are going to do will be, we could apply it to the equation of the summation. So what we are going to do here, individual x value will be 3 minus 3 multiplied by 5 minus 4. This is 1. The second would be plus 7 minus 3, 3 minus 4, plus it goes like this. So this whole addition will be the computation that you have to do under this section. Take the summation of individual those multiplications, divide by n minus 1 will give you the covariance. The x bar and y bar are defined similar to what we discussed last week. This is nothing but mean. Okay. You may see the practical applications of the mean and the coefficient of variance we are going to learn in a little while when we are doing the calculations, and you may feel the gravity and you may feel the as in the applicability of these values and what do they tell you and how to make decisions when you look at 1 or 2 examples which we are going to do in a while. Okay, so this is the first measure that we are going to learn under covariance, covariability. I'll recap. We initially recognize there are 2 types of relationships. It could be positive or negative under covariability. So now we are going to measure it by trying to identify statistical values for the covariability. The very first one, what we discussed a moment ago, is the term of covariance. I recap. The idea of covariance is how much two variables vary together for a given set of sample or a given set of population. Okay. The second indicator that we are going to learn here is denoted as correlation coefficient. Now, if you could recall that in our scatter graph also, we discussed that you may see some strong positive and strong positive, moderate and weak. The strength of the relationship in a visual manner. Under correlation coefficient, simple R, we are going to give it a numerical value. By computing R, you should be in a position to comment on the strength of the relationship in numerical terms. You can eyeball and say, okay, it seems to be a perfectly positive, seems to be a weaker one, but you need to have an indicator to tell how exactly or how precisely your your relationship is either strong, moderate, or weak. Okay. Having said that, let's look into the definition of correlation coefficient. It is a measure of strength of the linear relationship between two variables, that is, which is given by correlative coefficient or correlation coefficient. Both terms are mean the same thing. Simple R. I repeat, it is a measure of strength, the linear relationship between two variables. So how we define or calculate correlation is by taking the covariance of x and y. This one, covariance of x and y, divide by what is here, what is the root of variance, nothing but standard deviation. Isn't that so? So you have the variance here. When you take the standard deviation of that, when you take the the square root of that, we call it as a standard deviation. So we compute the covariance value for the given data set. You may see plus 20 or plus 100 or whatever the covariance by standard deviations of x's and x values and the y values together, which will give you the value for correlation. Now, unlike the case of now mathematically, if you compute the covariance, you may get categorically you may get different values, isn't that so? So the x's and y's may have positives or negatives. Some may get cancelled off. Some may have extremely positive values. Some may have outlier values. So the s square for xy could have a different range of values, which sometimes might not really uh, be comfortable for a comparison or for a final conclusion on the covariance of the two variables. However, when we take that covariance and divide by the variance uh, square root of individual x's and y's, value that we are getting as correlation coefficient will have a nice range of values from -1 to +1. We will be discussing that in the next slide. The important point to remember here is nothing but this equation. If you look at the values for covariance, you may simply replace this portion by applying the equation which is shown here, xi minus x bar to the multiplication of yi minus y bar. Take the sigma of that, divide that by n minus 1. Okay. And for the variance also, you may take the, for the standard deviation variance, what we denote is nothing but xi minus x bar divided by n, or in this case, if it is sample, n minus 1. You could do a simplification of those values of x's and y's, and the easiest way to apply those x's and y's are the form that you have been invited to keep in mind. This is the formula that you will be needing to keep an eye on at the examination. Unfortunately, I haven't seen in the question papers whether this formula is given. So in that case, I assume that you need to keep a note and keep this in mind for the application part. If you merely look at the formation of this equation, I mean, it's true that you have to keep in mind, but it might be difficult for you to keep a formula like this in mind. But if you just look at the formation, you may see this is nothing but, I mean, forget about the top part for the moment, but on the bottom part, what you could see is that you have the root n number of items, sigma x squares minus sigma x's. This 2 should be in the superscript form. That means this should be the power, not the multiplication. Sorry about that typo. So n sigma x square minus by sigma x. Now sigma x means the summation of 3, 5, 4, -1, the value. Let's say that summation will come up to 10 in that class example. So 10 to the square. So that's the idea of one side. The same for the y variable. So if you just keep in mind of this segment, you could double that by just replicating the values of the y's. So n sigma x squares will be replaced here by n sigma y squares, and minus, instead of sigma x, where you'll be adding up the x values, you may have to add up the y values. This is shown correctly. This should be similar to this. That's what I meant by here. On the top part, what you have is n sigma xy. Now this is individual values being multiplied. Now in that example of 3, 5, and 1 and 3, what you meant by this xy will be 3 into 5, 1 into 3, 7 into 0, so on and so forth. So those multiplications you have to sum up, multiply that by n minus sigma x and sigma y. So this is the formula that you can calculate the correlation of coefficient. Okay. Again, I reiterate the fact that towards the next day lecture, when we are doing the sum computation, we'll try to apply this formula, as well as we'll try to find some shortcuts of the calculator where most of these sigma x's, sigma y's, y square sigmas, x square sigmas can be easily calculated using the stat mode of any scientific calculator. We'll try to utilize a little time and learn that also. Okay. Again, I recap. We discuss one formula on covariance. The covariance is how two variables are varying together. Unlike a single variable, when we have x's and y's, we need to take a different formula to identify the covariance value. However, if you just compute the covariance for a given data set, we discussed that it's an absolute value. It may be giving different numbers which might be somewhat different and difficult to compare or come to judgments or conclusions. In contrast, when you calculate the correlation coefficient of R xy, you may find a relationship that whatever the R xy that you will calculate will have a value ranging from +1 to -1. This is what is important to keep in mind. +1 to -1. Now, for the values of Rxy to have a +1 or a plus value implies it has a positive correlation. You could recall in our graphs earlier, instances like this, positive correlation. If R to have negatives, -1 or closer to -1, this is the other class which will imply that the given data set the given data set of pairs, okay, x's and y's, will have a negative correlation. So I said that the data could be ranging from +1 to -1, um, inclusive of both +1 and -1. The other important numerical value in between this range will be 0, r equals to 0. When r is equal to 0, statistically, we could say there is no any linear correlation. Important word, linear, okay? When r is equal to 0, we could comfortably say no any linear correlation. Does it really mean that there is no correlation at all? There could be other forms of correlation, maybe curvy correlations, maybe circular correlations, maybe quadrants or logarithms, um, maybe complex numbers. There could be different correlations between these two given pairs. However, the Rxy that we compute for the correlation of coefficient, this formula, will only give a judgment or a conclusion on whether the given data set has a linear correlation or not. It's important to know that. Okay. Now, under these two segments of positive correlation and negative correlation, what we are going to discuss here is that whether the given data set has a positive correlation, negative correlation, and the degree of the relationship. If R is close to, if R is exactly +1, this is the definition of perfectly positive correlation. That means all the data points for the x's and y's, smaller x's, smaller y's, higher x's, higher y's. Okay, everything in those relationship could be recognized in a perfectly straight line where perfect positive correlation is recognized if R is +1. On the other hand, if R is -1, perfectly negative correlation. For the smaller x values, higher y's, higher x values, smaller y's, negative correlation, perfect. That means all the data points will again come to the same trend line, best fit line or regression line. This is also important to note. If R is close to +1, there is a strong positive correlation. If R is close to plus 0.5, we could recognize this instance as a moderately positive correlation. In our graphs of scattergrams, the middle one, moderate relationships, is evident when R is close to plus 0.5. Does it have to be exactly plus 0.5? It doesn't necessarily be. It should be close to plus 0.5. Let's say in exam you have been given R of minus 0.49. Where are you going to plot that? It's close to the middle point on the negative side. So you could denote that it is a moderately negative correlation. If R is close to -1, let's say minus 0.98, that is very much close to -1, isn't that so? So minus 0.98 would be an example of strong negative correlation. How about minus 0.01? Minus, I repeat, minus 0.01. Close to 0, but from negative side. These are instances where we are going to define as weak negative correlation. How about minus 0.1? Easy, weak negative correlation. How about, now this is a tricky question, minus 0.25? Are you going to categorize that as moderately negative or weak negative? Now all these values of, let's say, -2, -0.2, -0.25, -0.23, still you could cluster them as in the region of 0.5. The whole idea is that if it is close to 0, it has to be very much close to 0. It's a judgmental call where you could recognize that as a weak negative correlation. There's no earmarking of 0.25%, 50%, 100%. There's no hard and fast earmarking. However, an approximation is what we are going to take in for our judgments. So ranges that we are going to discuss, I reiterate, +1, -1 would be the two extremes. 0 is another interesting point for no relationships, and plus or minus 0.5, those 2 points are also some points of interest where we are going to demarcate for moderately positive or weak positive for correlation coefficients. Okay. So having said that, we have come to the conclusion points of the discussion on the entire segment of questions, where we have this entire segment of this session on the central tendency and dispersion. So for the so for the completion's sake, for your reference, I have just sum up some of the very frequent and importantly used equations here. Okay, the mean, why haven't I put the equation here? I mean, it's easy to remember, isn't that so? You add all the values of one variable, divide by number of occurrences, it would be the mean, or x bar. X bar would be always xi divided by xi sigma divided by n. You have 10 numbers, add everything up, divide by 10, which will give the x bar. Okay. But variance, covariance, coefficient of variation, covariance and correlation are the important equations that you are going to apply again and again when you are doing the examination questions. Have we seen complete questions? Of course, there are a couple of examples. The examiner has tested 1 or 2 complete questions talking about good 20-mark questions by merely asking your observations on a data set and asking you to compile these values of central tendency and dispersion, where you need to comment most of the time, where you need to comment 2 variables given for your observations, and asking, maybe examiner can ask you to plot a graph and visually identify the relationships, or examiner can give you a graph and ask you to comment on the evident relationships based on the face value of it. And then examiner can give you some values of for your independent variable of x and depending variable of y, and ask you to compile these indicators of variance, coefficient of variation, covariance and correlation. Before we wind up the class, I really want you to focus a little bit here and identify these equations one more time. And in the blue color, what I have given is the glimpse or the highlight of the those statistical indicators and their usage. Okay, let's take a moment. Variance, again, I reiterate, this is how data are spread around the mean value. Variance, for how many variables are we going to define? Simple, it's just one variable. Covariance would be the instance where you will be discussing the variance of 2 variables. Covariance, cohesion, or co-movements. So for the variance of individual or one variables, s square will be denoted as sigma I equals 1 to the nth. Now, students, it's important to note that when the best form to represent the statistical jargon would be to always take the sigma and write on the bottom side of it I equals 1. Last class I explained it to you. And at the top side, to the maximum point. So I equals 1 to simple nth would be the range. However, in these equations, you may have recognized that I have not earmarked that I equals 1 to n. Does that means that those are forgotten? It's not the case, but for the spaces and present in the slide only, I have omitted that, but I have just kept it here for the remembrance. Okay. So for the variance, I reiterate, you have to take the differences between the individual x's to the mean value and take the square of it. We discussed that to omit the negative variances. Previously in the mean deviation section, we took the modulus value. However, if we take the variance just for the computation sake, we take the square value. So the standard deviation would be nothing but the square root of this entire calculation. Isn't that so? So we take individual values, minus by the mean, take the square, take the summation divided by number of items in the sample. If this is population, the only difference would be instead of n minus 1, we divide it by n, total number of observations. So variance, the other equation which I have not written here is nothing but the standard deviation, which would be the square root of this. Okay. Then second, we came to the important equation of coefficient of variation. I repeat, coefficient of variation. Why do we came to this is that we identify by just looking at the values of variance and standard deviations or any of it, we may not compare two data series where it could even come to misleading judgments of the class examples which we discussed at the last lecture, where you may have same standard deviations values, but it doesn't really imply the nature or the scatteredness of the data. That's why we came to this indicator of coefficient of variation. The idea is that it measures the relative dispersion. Relative dispersion can be used to compare distributions. Okay, that's the idea. Then thirdly, we define now when we have more than one variable, we identify that instance as the two variable scenarios or independent and dependent variable scenarios. This is where the variance equation took a different form. Instead of taking the multiplication of xi minus x bar to the square, we could easily calculate the covariance by taking the xi minus x bar to that of yi minus y bar values and divide by n minus 1. Again, we are talking about the sample here. So this derives three types of relationships: positive, negative, and null or no relationship. But does it really give you any indication on the strength of the relationship? It could not. Similar to our variance discussion here, it may, when you do the calculations, we'll go into detail, don't worry. When we discuss the value for covariance, you may see different values, maybe 0, 3, 5, 10, 1,000. It will be again marginally difficult to discuss or compare the relationship between two or more data sets or multiple data sets or any data set for that matter. That is where again we wanted to define the last variable of coefficient of variation, the correlation coefficient. That is the last equation we learned under here, correlation. Correlation again stemming from two variable instances where it quantifies the strength of the relationships between the two variables. That typo that I explained is also evident here. This should be in the superscript form. That means sigma x2 square. Sorry about that. So this is the glimpse of today's entire discussion. Again, I brought the variance equation from the last week just for the completion's sake. So we had one variable. We computed the variance and the standard deviation. We identified how that variable's values are being dispersed from the value of mean. Then we recognize that it's not going to be sufficient. You can't compare things. That is where we introduce this relative measure of coefficient of variation. Take the standard deviation, divide it by the mean value, take the percentage of it, and easily you could do comparisons. Then we introduce two variables of x's and y's, where the same variance formula, we have marginally modified it to a different form, and we introduce the covariance formula as depicted here. Lastly, for the covariance also, similar to variance, just by computing, it's difficult to come to conclusions. You can calculate the covariance, take the value. However, there are more things to be, more decisions to be made in statistics. So that is where we need to identify the strength of such covariance also. To identify the strength only, we have introduced the correlation coefficient R, xy. That's the entire theory part of the lecture 3, both 1 and 2. Before we wind up today's class, I have just caught one question from 2016 March paper. Okay, I'm going to take a moment here, and we are going to discuss this question just to show you how keen examiner are going to test your knowledge on the areas that will be questioned under central tendency and dispersion. Let me quickly pull up the paper of 2016 March. I'm talking about question number 3. Okay. Now, as I explained at the beginning of the lecture, now we are done with the theory. We have covered the entirety of the theories to be tested at the examination under central tendency and dispersion with this part. However, there are plenty of questions to do. Our statistics is all about numerical computation. So we are carrying forward some questions which we could not discuss under lecture 3.1 last week. Similarly, there are plenty of questions under 3.2 where covariance, coefficient of variation will be discussed in a separate class, ideally in the next class. Okay. But for the completion's sake, under the theories that we learned today, let's discuss this question and wind up the class for the day. I'm pulling up 2016 March paper question number 3. Look at the question. Following scatter plot shows, scatter plot means a scatter graph, shows demand for electricity in y-axis and average daytime temperature in x-axis. Demand for electricity in y-axis and average daytime temperature x of a city for 30-day period. Now, the statistician who has plotted these scatter points is trying to identify whether there is any relationship between these two variables of one, electricity demand, second one, temperature for given 30 days. Even when I read that question, I was feeling a little uncomfortable with can we identify any correlation between those two values? That's what we are going to see. Simple as that. You may find a relationship, you may find a correlation, or you may not find a correlation. However, examiner has given you some scatter points like this. The first question he's asking, is there any relationship between the demand for electricity and the average daytime temperature? Briefly discuss your answer. Here, what is merely expected by answering this part would be just to eyeball it, just to look at the scatter points and identify this relationship. Can you comment on whether it's a perfect positive? It's difficult, isn't that so? If it is to be perfect positive, you need to have all the scatter point, which you will put a ruler and draw a nice line. It is not the case. However, if you just eyeball it from x-axis to y-axis, when the x values are smaller, you may see smaller y values. When x values are larger, see larger y values. So this is a classic example of positive relationship. So this means that higher the temperature, more power is used. So what could be one of the possible reasons may be air condition, isn't that so? So for air condition in that city, maybe they have plenty of air conditioning in use, building heating. Mm. So when the temperature x-axis is going to rise, the electricity demand is also going to rise extensively. So that would be your brief answer. You could elaborate it like that. The first important point, there's a positive relationship. Second point, the implication would be higher the temperature, the more the power is used. Second question, does this mean that average daytime temperature actually causes the demand for electricity? Explain your answer. Now, this is where you have to be careful and creative. Does this mean that average daytime temperature actually causes demand for electricity? Okay, actually causes demand for electricity. Okay. In practical sense, when you just take two variables, you may see a correlation. But given otherwise, can you say only those two variables that we are discussing have exactly caused the movement of the dependent variable because of the independent variable's move? That might not be the case. That's what examiner's answer is also suggesting. Merely we can say broadly, just by looking at the pattern, we could say these two variables are correlated or related. That's fine. Correlation tells you that one variable, temperature, changes. The other, demand for electricity, seems to change in a predictable way. However, you cannot say that one of them causes the other. The x-axis, I repeat, daily temperature has causes the y electricity demand. Could there be other variables? Of course. Maybe, similar to temperature. What about the rainfall? What about the uh, um, population of that city? Population may vary. You may get some visitors, you may have less visitors. What about the working hours? What about, let's say, weekends and weekdays? Could be due to different factors of the day's activities on that town, it could cause electricity demand. What if they had a concert? What if they had a, let's say, some electricity heavily using events like Vesak, for instance, where you will have a lot of bulbs being put up. Ironically, that day, the Vesak day, you may have a higher temperature also. Does that mean that higher temperature has caused the electricity demand? It might not be the only cause. So that's the broad answer. Then, if you look at the third part, you need to calculate the correlation coefficient R. This is the last equation that we discussed under today's lecture, Rxy, for a 6-day period, n equals 6. Okay, where now if you look at those numbers, what examiner has given are the exact numbers of sigma x, sigma y, sigma x square, sigma y square, and sigma xy. Now students, if you look at this, what you could determine is that if you could keep that equation in a corner of your mind, you could easily score 5 marks here. This is nothing to be written on opinion, nothing to be written on judgment or explaining, just by applying the equation that we learned a moment ago on correlation coefficient. That is the answer for this one. Don't worry, we'll discuss the answer again when we do the Q&A next time. The answer would be, I'm quoting from the examiner's answers, suggested answers. The answer for R xy is calculated as 0.903. What do we have to do here is merely take these values and plot it to the equation of Rxy. So have you given the equation? Unfortunately, no. So you have to keep that in mind. So the answer for the 5 marks of correlation coefficient of Rxy is calculated as 0.903. Now, if you could recall, the values for R has been ranging from +1 to -1, with important points being +1, +0.5, 0, 0.5 negative, and -1. Okay. So the answer that we are getting for part number 3 is plus 0.903. Where is it close to? It's going to be close to +1. We'll keep that in mind. Let's look at part number 4. What are the important things correlation coefficient tells you? What are your conclusion when the correlation coefficient become plus 1.00? Now for this answer, what you have to write here is that first, you can call the theory part. You can call the theory part on the correlation coefficient. If I just had a glance on the examiner's answer, it says correlation coefficient tells the direction of the relationship. Okay, it could say the positive or the negative. Now in this one, plus 0.903. If your correlation coefficient is a positive number, then you know that you have a positive and the negative otherwise. This means that as one variable increases, the x variable, in our example, the daytime temperature, then when that increases, the value of the other variable, that is the demand for electricity, tend to go in the same direction in a predictable manner or vice versa. Larger correlation coefficient mean that stronger relationship and vice versa. That means a smaller number, if you get it for part number 3, that means a smaller correlation coefficient. Lastly, now again you can comment on plus 0.903 seems to be a strong, positive, or moderately strong, depending on your judgment. That doesn't really matter. You can come to your conclusion with your argument. However, examiner is asking, what is your conclusion if the correlation coefficient become +1? That is where the theory that we learned a moment ago, when there's a positive, perfectly positive relationship for the two variables, this means that the value of one variable increases, there is a perfectly predictable increase in the value of the other variable. How much from what end to the other end is going to be discussed under the upcoming sections on regression, coefficient of determination, and etc. So this, what we discuss right now, is a complete 20-mark question. Now, there are some other questions also in the past papers, and if we can find more time, we shall bring in some more other questions which is available on other curriculums also, just to give you some practice onto the computation of correlation of coefficient, variance, and some other important formulas like coefficient of variation and covariance, and so on and so forth. So the important take-home part from today's lecture would be the slide that I have shown here, the summary. Okay, from last lecture to this lecture, mean, median, mode, I hope that it is carved in your minds right now. We discussed the importances, weaknesses, applicability, and then we discussed variance, standard deviation, coefficient of variation for single variable. Today's lecture, we discuss some qualitative aspects of this data of single variables under segments on kurtosis and skewedness. It doesn't really need to go for computations, but what you need to keep in mind is the shapes and their respective names to be applied on the theoretical knowledge, categorical MCQ questions, and some elaborative opinions also. Today's lecture, we concluded with identifying two main statistical indicators for two variable scenarios, independent and dependent variables of x's and y's, where data pairs of xi's and yi's could be applied for these two equations of covariance and correlation of coefficient to identify the indicators on s square xy or rxy. Why do we calculate? To identify the one is to identify the types of relationship, positive, negative, or no relationship under covariance. And when you calculate the correlation coefficient, we are looking at identify the strength of the relationship of two variables. That's the summary for the day. And I hope we have discussed what we are going to do for the next lecture. We are a little ahead of time on the planned lecture schedule. So we will be discussing all the questions that is under syllabus area number 3 on central tendency and dispersion on the next lecture, after brushing up of your knowledge on lecture 3.1 and 3.2 again by taking 10-15 minutes of your time. So thank you for your time, and be prepared with the examination questions which I shared last week also. There will be a few more questions under this section which we discussed today. We'll discuss everything on next lecture and complete this segment. I repeat that this is an easy question to score marks compared to other areas. All what you have to do is that keep in mind of the summary slide in your mind. Okay. Thank you.